Okay, coming to the first topic of our last module, module 5, specific energy and specific energy curve or specific energy diagram. It's also known as specific energy diagram. So, the total energy of a flowing fluid per unit weight is, we know this, right? That is the datum head plus pressure head plus velocity head or kinetic head. In the case of open channel flow, we have already discussed that the pressure head will be represented by its depth of flow. Okay, where Z is the height of the bottom of the channel above the datum. So in this figure, everything is marked. This is our datum, this horizontal line. Below the channel bottom, we are taking the reference line, datum. So the height of the bottom of the channel from above the datum is Z. Okay, it's marked as Z. This is our channel bottom. This is an open channel flow, and this much is the depth of flow. That is H is equal to the depth of the liquid or the fluid, and this is its free water surface. Okay, and above that there is the kinetic energy head or the velocity head, which is represented by V square by 2G. So if the channel bottom is taken as the datum, what will happen? This Z term won't be there, right? This channel bottom will be the datum. So Z is equal to 0, and we'll get E is equal to H plus V square by 2G, and this is nothing but specific energy. That is, specific energy of a flowing fluid is defined as the energy per unit weight of the liquid with respect to the bottom of the channel. Okay. Specific energy, we always say with respect to the bottom of the channel. Therefore, the channel bottom will be taken as the datum. Hence, Z, that is the height from the datum to the channel bottom, will be 0. So, we'll get a term like H plus V square by 2G in the total energy, and hence this term is known as the specific energy. Okay. Now coming to the specific energy curve. So this is there in your series test. You have to derive this. Okay. So please listen. Specific energy curve. Curve which shows the variation of the specific energy with the depth of flow. It is nothing but a curve which is showing the variation of the specific energy with the depth of flow. If I show you the curve, see, this is the specific energy, this, and showing the variation of the specific energy with respect to the depth of flow. Okay. Now we'll get a curve like this. This is our specific energy curve. So how will we get that? That's what we are going to discuss. So we know that specific energy is equal to H plus V square by 2G. And this is what, this term is the potential head, right? This depth of flow is nothing but the potential head or the potential energy, and V square by 2G is nothing but the kinetic head or the kinetic energy. Okay. And it is marked as, oh, this is not V, okay, this is K. You have to mark it as K. So EP, we'll get E is equal to EP plus EK. Where EP is the potential energy of flow, that is H, and EK is the kinetic energy of flow, which is equal to V square by 2G. Now, consider a rectangular channel in which a steady but non-uniform flow is taking place. So, this is our assumption. Okay, what is the steady flow? We know that dou V by dou T will be 0. That is with respect to time. There is no change in velocity. Okay, and what is a non-uniform flow? That is with respect to space, the velocity is changing. Okay, so our assumption is this is a steady and non-uniform flow is taking place in an open channel. So where Q is the discharge through the channel, and B is the width of the channel, H is the depth of the flow, and small q is the discharge per unit width of the channel. So what is the small q? Discharge per unit width. We know capital Q is the discharge, and width is B. So Q by B is equal to constant. Okay. Now, what is this B? This is the channel width. Okay, this is not the free surface. This is the channel width. And above that, the water will be flowing. Okay, this is the channel width. This is B, channel width. Now, they're saying that this discharge per unit width of the channel is a constant. Okay, so V is the velocity of flow, and we know how to represent that, right? Q is equal to AV, so V is equal to Q by A. And what is A? A is nothing but width into depth of flow. So V is equal to Q by BH. What is this capital Q by B? We have already represented it as small q. So we can represent this capital Q by B as small q. Now we get something like B is equal to Q by H. Okay. Now putting this expression in our equation 1, we'll get something like this. That is E is equal to H plus V square by 2G. This is nothing but H plus. We are representing V in terms of Q and H. Okay. H plus small q square by 2G H square. Which is equal to potential energy plus kinetic energy. Okay. Now, this equation 2, that is this equation 2, it gives a variation of the specific energy with the depth of flow, isn't it? That is, in this case, there was only one term which was varying with the depth of flow. But when we represented like this, we got both the terms in terms of depth of flow. So this equation gives the variation of the specific energy with the depth of flow, that is H. That is, the potential energy is also represented as H, and the kinetic energy is also represented in terms of H, or the depth of flow. So for a given discharge capital Q, for different values of depth of flow, the corresponding values of E may be obtained. Okay. So what we are doing is, for a given discharge, that is the discharge here, we are taking it as constant. For different values of depth of flow, as the depth of flow is increasing or decreasing, the corresponding value of the total energy, or the specific energy, is being plotted. So this is the specific energy, this is the depth of flow. So we know that the depth of flow is increasing. Okay. And it is making an angle of 45 degree. So we are getting a line like this in the case of the potential energy, that is, as we are moving, we are assuming that the depth of flow is increasing. Okay. Now coming to the velocity head, we are getting a curve like this, q square by 2g h square. This is a parabolic equation, isn't it? This is a parabolic equation, so we'll have to represent it like a parabola. Whereas EP is equal to H, this is the equation of a line. That's why we are getting a line like this. Okay. Now this is EK and this is EP. Now combining these two, we'll get the specific energy curve, isn't it? So EK at this point, we can see that it is q square by 2g h square, and EP is equal to H. Now combining these two, EP plus EK, we'll get a curve like this. Why we are getting a curve like this? Because at all these, when the as the specific energy is increasing, we can see that the value of kinetic energy, this is the value of the kinetic energy, right? It is going like this, plus H will give you something like this. So at every point, if we plot this and add these two, we'll get a curve like this. So this is our specific energy curve. I've marked everything. So we can see that now there are some terms known as critical depth, alternate depths, etc. So the derivation will be until here, but you have to say what is critical depth, alternate depths, etc. You don't have to derive all this expressions for the critical depth. You just have to say critical depth is this much, critical velocity is this much, and alternate depths are this much, and you have to mark the alternate depths like this also in the derivation of the specific energy curve. Okay, so now I'm going to say what is critical depth, alternate depths, etc. Okay, now critical depth is the depth of flow of water at which the specific energy is minimum. That is the depth of water at which the specific energy is minimum. To get anything at the minimum, we have to differentiate it with respect to a variable and equate it to 0, isn't it? So this is the d by dh of E is equal to 0. This is the condition for the minimum specific energy. Now d by dh of E is H plus q square by 2gh square is equal to 0. When we differentiate it, this is H, right? We'll get it as 1, and q square by 2g is a constant. We'll take it out. And 1 by h square, if we differentiate it with respect to h, what will we get? We'll get minus 2 by h cube. And equate this to 0. Now 2 and 2 gets cut off. We'll get 1 minus q square by g h cube is equal to 0. That is 1 is equal to q square by gh cube, or h cube, h goes here, h cube is equal to q square by g. And if we represent h, we'll get something else. H is equal to q square by g the whole raised to 1 by 3. So this depth is known as the critical depth, wherein the specific energy is minimum for a depth of flow. Okay, so that depth of flow where the specific energy of minimum is nothing but critical depth, and it's obtained as q square by g the whole raised to 1 by 3. Okay, so at this curve we can represent this point as the critical depth, isn't it? This is the point where the specific energy is minimum, and it is noted as the critical depth. This is the minimum point this is the point where the specific energy is minimum. Now coming to the critical velocity. The velocity of flow at the critical depth is known as the critical velocity. So the velocity possessed by the fluid at the critical depth is nothing but the critical velocity. So we know hc is equal to q square by g the whole raised to 1 by 3 is the critical depth. So hc cube, if 1 by 3 goes here, we'll get hc cube is equal to q square by g. We can write it as g hc cube is equal to q square, and this we are expressing it as the equation number 1. And we know small q is equal to capital Q by B. And what is capital Q? Q is equal to AV, right? VA by B. And V, and again A is what? Depth into width, that is B into H by B. So this B and B gets cut off. We'll get small q in terms of mean velocity and depth of flow, that is Q is equal to VH. And we are substituting this value of Q in our equation 1, which this is our equation 1, right? That is GHC cube is equal to Q square. So we are substituting the value of Q, that is VH, in this equation 1, that is GHC cube is equal to Q square, that is VH square. And at the critical depth, everything will be in terms of critical depth. Okay, so VC is the critical velocity, HC is the critical depth. So we'll represent it as GHC cube is equal to VC square into HC square, where VC is equal to square root of HC, and HC square and HC square gets cancelled off. We'll get HC here, and if we take VC, we'll get it as the square root of G into HC. Okay, so VC, that's the critical velocity, is square root of G into the critical depth. So the minimum specific energy in terms of critical depth is, we know this is the equation for the minimum specific energy, H plus Q square GH square. And at the minimum specific energy, what we know is it is possessing a critical depth, right? So we can mark everything in terms of critical depth. So E minimum is equal to HC plus Q square by 2G HC square, where HC is nothing but Q square by G the whole raised to 1 by 3. Therefore HC cube is Q square by G. So E minimum is nothing but HC plus Q square by G is here, right? In this term there is Q square by G. I am substituting HC cube there. So HC plus HC cube by 2 HC square. HC square and HC square gets cancelled off. We'll get 3 by 2 times HC. That is E minimum is equal to 3 by 2 times the critical depth. So minimum specific energy we'll get when depth of flow is equal to 1.5 times. Sorry, E minimum is occurring when is equal to 3 by 2 into HC. At this point, we'll get the minimum specific energy, or we have written everything in terms of the depth of flow. Okay, and depth of this critical depth is nothing but the depth of flow at which the specific energy is minimum, and that condition is equal to 3 by 2 HC. Now, what is critical flow? Flow at which the specific energy is minimum, or the flow corresponding to the critical depth, is known as critical flow. So, everything we are representing in terms of critical depth. Okay. First one, we found out what is critical depth. Next, we found out what is critical velocity, the velocity of flow when the depth of flow is at critical depth. Okay, that is nothing but the critical velocity. And what is critical flow? Flow at which the specific energy is minimum, or the flow corresponding to the critical depth. Everything we are representing in terms of critical depth is known as the critical flow. Now we know VC is equal to root of GHC. So Vc by root of GHC is equal to 1 is the condition for the critical flow. Okay. And this term, that is Vc by root of GHC, is nothing but the Froude's number which we have discussed in the earlier module. Okay. Froude's number. And we have discussed critical flow, subcritical flow, supercritical flow, etc. Just we have gone through the basics. So this is how we obtain it. Vc by root of GHC is equal to 1 should be the condition for the critical flow. For a critical flow to be happening, Vc by root of GHC should be equal to 1. And this term Vc by root of GHC is represented by the Froude's number. For the Froude's number, that is Vc by root of GHC, it should be equal to 1 for a critical flow. So when the Froude's number, that is the Vc by root of GHC, is equal to 1, will give you the condition for the critical flow. And based on this Froude's number, the different types of flows in open channel can be classified as the critical flow, then there is subcritical flow and supercritical flow. Okay, that is if the Froude's number is less than 1, that is Vc by root of GHC is less than 1, also the depth of flow is greater than the critical depth, then it will yield a straining flow or a subcritical flow or a tranquil flow. And if the Froude's number, that is Vc by root of GHC, is greater than 1 and the depth of flow is less than the critical depth, then it will yield a supercritical flow or a shooting flow or a torrential flow. Okay. And what are alternate depths? Now, in a specific energy curve, except for the critical depth, for any other value of specific energy, there are two depths. One greater than the critical depth and other smaller than the critical depth. So these two depths for a given specific energy are called alternate depths. So if we look into this figure, we know this is a specific energy curve, isn't it? So other than this critical depth, this is the point where the specific energy is minimum. So here we are marking it as the critical depth Hc. Okay. Other than this critical depth, every other point in this specific energy curve, it will yield two alternate depths, isn't it? See, at this point H, we are getting H2. This is the depth H2, and at this point G, we are getting H1. So for a given specific energy, see the specific energy at G and H is same, isn't it? For a given specific energy, we are getting two values of depths from the specific energy curve, isn't it? Which is H1 and H2, other than the critical depth. For at this point where the specific energy is minimum, we are getting only the critical depth, that is Hc. But other than that, we can see that if we plot any values for the specific energy, if it is here, we are getting two depths. If it is here, if the specific energy is here, we are also getting two depths. So for any values of specific energy, we are getting two depths, isn't it? For a particular value of specific energy, we are getting two depths, and these two depths are known as the alternate depths. So you have to mark this alternate depth also in the specific energy curve when the derivation is asked. Okay, but you don't have to explain everything. Just explain what is critical depth. You have to mark C, that is the critical depth. You just have to write this expression, and also you don't have to say all these values. Also you have to mark this alternate depths in this specific energy curve. You have to mark the alternate depths also. Just plot some specific energy and mark it as H1 and H2 and say it as alternate depths. That's it. If they are asking for the derivation or to explain the specific energy curve, that's what we have to do. Okay.